Hello, this is the first video of topic 2.5, 2.6. But before we get into 2.526, I want to remind you of what you were doing before we got here. And it goes back to this idea that we can find the derivative function. We can find the formula that will find the slope of the tangent line, the derivative value, the instantaneous rate of change at any x value by doing this limit definition, the limit definition that says we're going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. Got it. Cool. So what I want to do in this first video is maybe walk you through that again. We did it already, but I want to create some samples that are going to lead us to a pattern, and then that pattern is what this set of videos is really all about. So I'm going to try to do this quickly. Let's start with this. Suppose let f of x be 5x to the second power. 5x to the second power. Yes, we're going to find f prime. So finding f prime means we're going to take the limit as h approaches 0 of the function evaluated at x plus h. So we're going to take this function and we're going to evaluate it at x plus h minus the original function given, f5x squared, all over h. And we're taking the limit as h approaches 0. Now, again, if we try to do direct substitution right now, we're going to get an indeterminate form, so we need to do something else. And so in class, one of the steps that you all were doing was simplifying, and I say simplifying even though in reality it looked like it got worse before it got better. We're simplifying the numerator, right? So we're going to square this out. So I have 5 times all of this squared. Now I'm going to tell you something that I told the other group, which was I think the way we did it in class was x squared plus h squared plus 2xh minus 5x squared. So I know that we talked about being precise with our work so that everything links mathematically correct, right? I don't want to put a limit here, then all of a sudden the limit disappears and I'm only working on this, especially if I put equal signs, because then it just doesn't make sense. And the student a student might argue, well, then don't put equal signs, then it's not the same. True, but then the reader, whoever's grading your work, can't really follow like where you're going. At least here we're saying, hey, the derivative is equal to this limit definition. Oh, by the way, we're still taking the limit, but I've simplified it. Oh, but do I have to show every step? I don't, right? I could have, at this point, I could have done all of this and just have written 5x squared plus 5h squared plus 10xh, right? I could have done that. I could have skipped a step here or there, but I guess what I'm asking you to do is make sure that whatever you write, does it flow? Would it make sense to someone who doesn't know you, who's reading your work for the first time? Would they be able to follow from A to B to C, steps A to B to C, and get to the answer so that everything's mathematically correctly linked, I guess. So I distributed the 5, multiplied everybody by 5, boom, and now I'm going to try to reduce. The tip is when we're doing the limit definition, whether it's h approaching 0 or whether it's x approaching a value, is that I know I'm on the right track if the second term in the numerator vanishes. And it's about to vanish in this example because I have minus 5x squared plus positive 5x squared. It is going to vanish. So we're going to continue. And I'm going to do the limit as h approaches 0 of, and here's a good example. I could write 5h squared plus 10xh over h, but I already see that there's only 2 terms left. They both have an h, so why don't I just factor it out now and do 2 steps at once? Because then I know that I'll be able to reduce the h's, and now I can evaluate the limit by plugging in 0 in for h, not for x. And when I do that, If I plug in 0 here, I'm left with this. This tells me that the derivative function is 10x. And what that means is, if I ask you to find the derivative value for this equation, or this function 5x squared, if I say find the derivative value at x equals 1, all you have to do is plug a 1 in there and it's going to give you the derivative value. If I ask you for the slope of the tangent line for this function at x equals 3, all you have to do is plug a 3 in there and it's going to give you the slope of the tangent line. If I ask you for the instantaneous rate of change of this function at x equals negative 2, then you just substitute a negative 2 in there and it's going to give you the instantaneous rate of change. So the whole idea here is we're building a formula that finds the slopes or the derivative values for a specific function there. But it puts it in a form where I can find whatever slope at any given x value. We're going to come back in video 2, and I want you to see if you can find some patterns in the work that we do.